How can we check this stability? We will say, okay, if the input is limited to a value like A, how would be the output? So xt squared again would be limited to A. Yeah. So xt is again limited to A. So that's stable. Yeah. If input is a bounded or limited value, output would be bounded or limited value. How about invertibility? Is it invertible or no? What was the condition for invertibility? A system has inverse if for any input we only have one output. Here I have xt squared. You see y minus 1 is x1. y1 is again x1. If this system has inverse, how I can find x minus 1 from its inverse? We never can find it, yeah, because it never goes to out, which I can find it throughout. So this system is non-invertible. Okay, this was about properties. After that, we focused only on LTI system. In LTI system, if what is going on here, right? Confused. Okay. After that, we focused on LTI system. We mentioned the advantage of LTI systems is, what is the advantage of LTI systems? We can predict the output regarding to input if there is a exact. If we have the impulse response, what is impulse response? If I apply unit impulse and oh, it's connected here. You can see, but I think it has one. If we apply unit impulse, the output, we will call it impulse response. If we have impulse response, we can find the output to any input. How? How can you find the output to any input convolution? It was minus infinity to infinity, x tau is t minus tau, d tau. Or no, you can change h and shift x. T minus tau, d tau, h tau, d tau. We can use this convolution to find any output regarding to any input we have. Okay, suppose I have a system. They told me ft is like this. This is ft. What is ft? A step response. If ft is like this, they ask us find the answer to how would be the response of system to this input ht. What should I do? Should I don't have impulse response. That's an impulse. That's step response. You know, it was impulse response. If I apply step, we call it ft, step response. Now I have s. How I can find the output to this xt, one rectangular that has a square from 0 to 1. How can we find? Yeah, but in general, when you want to find the output, you should have input and impulse response. Do you have impulse response? We should find the impulse response. Do you remember what was the relationship between step response and impulse response? Exactly. Ft was ht. Impulse response was derivation of step response. What is the derivation of this waveform? Let me write here 1, here 2. Yeah. From 0 to 1, its slope is 1. From 1 to 2, its slope is -1. After 2, it's 0. So this is ht. Now we need to find the convolution between ht and xt. Can you do it? I want to check. Do you remember or not? We had 2 examples here. My expectation is we should be able to solve it. And the ones who are online, I would appreciate if you can try and see you can find it or not. At the same time, I can hear your voice. If you have any comment, any idea, please feel free to share. Can you hear me? Because no reaction is here, so I have no idea about it. No video. Something is wrong. Yeah, I know. Probably there is a timer, but I cannot find where is the timer. I didn't set any limit, but I'm not sure if there any setting or no. Okay, the ones who are online, please try to find convolution of these two signals, xt and ht. And I think you can share your paper. We will check together. Which one is easier for you to ship? Xt. At first, we should provide x tau, which is just changing the t to tau. After that, I need to find x tau plus t. Which means I should. You are doing by yourself. It's okay. I'm doing for myself. Anyone could solve among those who are online? Um, it's- okay, let's go. Anyone could solve? Yeah, let's solve together. Okay. At first, I tried to find x t minus tau. For that, we learned. At first, we should do time shift. I shift the shape t units to the left because now I consider t as a positive here. So after that, I need one time reversal, which would be like this. And this is h tau. If t is smaller than 0, you can see this would be x t minus tau. And this is h tau. I need to multiply them together. There is no overlap, yes? For t smaller than 0, h tau is 0. For t bigger than 0, xt minus tau is 0. So their multiplication would be 0. I move xt minus tau a bit further. How much? It comes like here, which means t comes here, here would be t minus 1. Yes, so t would be bigger than 0, but smaller than 1. Yes. On that case, we need to find this area. How much is this area? If you want, you can write the integral ht minus tau h tau d tau. Their overlap is from 0 to t. So this should be 0 to t. How much is x t minus tau? Its amplitude is 1. How much is amplitude of h? Again 1. D tau, which means tau 0 to t, and yt should be t. You can find it from this area, yeah? That's a rectangular. This side is 1, this side is t. Its area is their multiplication. I move t a bit more. Like it goes here. Here we have t, here we have t minus. So here is 1, here is 2, which means t should be smaller than 2, bigger than 1. How much is the overlap here? So again, t is minus infinity to infinity e t minus tau h tau it. How much is the overlap from 1 to t? Yeah, 1 to t. How much is amplitude of x? 1. How much is amplitude of h? Minus 1. Here the amplitude of this is h. It's minus 1 theta. So it should be minus t minus 1, which is 1 minus t. Again, I try to move x a bit more. Which one? Oh, my bad. You're right. But what did I do? I forgot that part. Thank you very much. From 1, we have this side and this side, both positive. 1 to t. Let me write like this. We have two regions. From t minus 1 to 1, how much is x tau? X1. And how much is h1? D tau. Plus from 1 to t, it should be 1 multiplied by h tau, which is minus 1 d tau. So it would be 1 minus t minus 1 plus 1 minus t, which is 3 minus 2t. In the border, there should be same. If the border is now, I should connect this one. After that, I should go connect that one. No, but At the border, for example, border here is t equal to 1, yeah? Border of these two regions. Y1 here should be equal to Y1 here, yeah. At the border, it should be continuous. Here Y1 is 1, here Y1 is, again, 1. Okay. That's for checking if you are doing well or not. If I move xt minus tau a bit more, which is going like this. Here is t minus 1, here is 2, here is 1. The overlap area is here. Yeah. If we write y, the boundaries would be from t minus 1 to 2. How much is xt minus tau? Exactly 1 multiplied by minus 1 d tau, which is 2 minus 2 plus t minus 1, which should be t minus 3. This is when t is, I think I made a mistake. Let me try one. Minus t. It should be, I think this is wrong. It should be minus, I can write t minus 1 minus 2. Which is t minus 3. Yeah. Am I correct? But at the border, if I write t equal 2, yes, correct. Both minus 1. If I replace t by 2, this one would be minus 1. Here, again, minus 1. That's correct. I was checking border at the beginning. I thought they are not the same. And last region, when t is bigger than 0. We don't have any overlap, so y t is big. So now we have y t for all t's, for all regions. That's response of this system to one rectangular signal. That was what we had last session. Today, we won't go through continuous time Fourier transform. At first, we just go a bit through signal space. We want to just give you one introduction how we find Fourier transform. After that, we go to Fourier series and Fourier transform. Why Fourier is important? Any idea? Yes. One of the reasons is, as you saw, for time domain, we should do convolution. These inputs are really simple input. If input is a bit more complicated, it's not easy to find the output. So when you go through Fourier transform, which means you are changing the domain from time to frequency. Do you remember the last topic of electrical circuit we had? Phasor. Did you see what happened in phasor? If you remember, we had, for example, for RLC circuit, what we had when we wanted to solve it, it was one second order equation, yeah? But we said we can move them to phasor domain. What will happen to this one? It will be algebraic. Yeah? J omega squared dy plus alpha j omega plus beta y. For sure. The next chapter is Laplace transform. Yeah, but the application is different. Yeah, we use Fourier transform to deal with the signals in frequency domain, but Laplace usually we use it for system. You will see for analyze stability. Fourier transform cannot analyze it. It cannot define the signal they are flowing. So one of the advantage of Fourier transform is we can change our differential equations to algebraic equations. That's much easier for us to solve this kind of equation. On the other hand, you will, what happened? Okay, press is F3. That's new. I think the problem is with this. Yes, that's new. I think I need to initialize it. Start the timer, it goes to screensaver, so we got it last night. I didn't have time to initialize that. What happened? Oh, but I am still connected. Cannot. How could I find the password? Here, the password. should be able to see here, yeah. Gonna have 5 minutes. Something happened with that. It cannot detect the Wi-Fi. I cannot link to mobile Wi-Fi, so I cannot share my screen. Things for the let me try this now. Something is wrong with network. Okay, now Devant, hold on, can you hear my voice? continue. I cannot see your feedback. Okay. The main reason from going from time domain to Fourier domain is simplicity. We can easily solve equations, algebraic equations, rather than differential equations. On the other hand, we will have intuition. You will see a bit further that when we are in a frequency domain, you can easily detect the signal. Yeah. In the last session, I think I showed you if we combine several sinusoidal signals, you cannot see in the time domain what is happening. But in the frequency domain, you can easily detect how many sinusoidal signals you have. Like vector space, we can define some operations for signals, like we call it as a inner product. When you multiply a signal by two signals, one of them conjugated, another the original one. You multiply it by them and take it integral from minus infinity to infinity. If they are periodic, we need to do this in one period. What we are looking, we want to define all signals through these definitions. If the inner product is zero, the signals are orthogonal. Yeah. And the size of signal we can write by inner product of a signal by itself. And if the inner product, the size is 1, we call it unit signal. This set of signals, if they have these properties, we call them orthogonal. If the inner product with themselves is 1 and with different one is 0, we call this set of signals as a orthogonal signal. One of the most important orthogonal set is this one. You know, for the different values of the k, if you multiply phi k, if you find the inner product by phi j, it would be 0. Only if these two are, for example, phi k, we will have a value. So what is the point? At the end, we want to show, since this is an orthogonal set, I can write any signal through a set of these signals. For example, suppose e to power of ft, if I apply it to LTI system, the output would be exactly the same of it. Yeah. Only it would have one coefficient. Yeah. We call e to power of ft as the eigenfunction, which means if we apply it to a system, the output is exactly like input, only one coefficient is different. We can prove it. We can just write the convolution. That's the LTI system. We know impulse response, we know input. If you apply convolution, at the end we will have one integral. This is independent of t, yes? You cannot see any t inside. So that's a function of f. We can call it as k. So we applied e to power of ft, and we found the output k e to power of ft. So in this case, if since system is linear, if we have e to power of s1, the output would be like this. Since that's linear, we can add all eigenfunctions together and find the the corresponding output. If it has ut, it won't be eigenvalue eigenfunction anymore. Okay, we can define any signal by these eigenfunctions. If we have a periodic signal, we define continuous Fourier series like this. You had this in signal and system and another course. Did you have mathematical engineering? No? You will see in one of your math courses for sure. Yes. And let's calculate 2. Maybe the definition for us, they call it something mathematical engineering, but for you that's calculate 2. Yeah. Yeah. Then you saw the different version, yeah, sine and cosine version. Here we have exponential. So if we have any periodic signal, we can define them with some exponential functions like this. We only need to find AK. Do you remember the first session I show you one square wave and I try to generate it with different sinusoidal signal? Do you remember that? Don't remember. Okay, we will do it again today. I mentioned it that Fourier series, how we find the amplitude of these signals. You didn't answer, yeah. You didn't know how I set the amplitude of these sinusoidal signals. Yeah, it was based on the Fourier series. We can find any periodic signal equal to this series, and we just need to set to find a the coefficient. Let's see how we do that. I have a periodic signal here, xt. The value is 1 when t is between minus t1 and t1. I know I can write xt is equal to k minus infinity to infinity ak e to power of jk omega 0 t. What is omega 0? Like 2 pi over t. Here I should write t1. Here I should write in this shape. What should I write t? The capital T. What is the main period? Middle one, which is how much is it? You should be able to find it through t0. Yeah, it's periodic with t0. So I just need to find AK. The relationship of AK is like this. I need to write 1 over T0. Integral over 1 period. Suppose we are taking integral from here to here. From here to here, it's 0. So I have only value from minus T1 to T1. Xt, which is its amplitude is 1, multiplied by e to power minus jk omega 0 t dt. Integral of e to power of alpha t dt 1 over alpha e to power of alpha t. So here, integral of e to power of minus jk omega 0 t, I need to bring these coefficients to denominator. So if I just set t1 and minus t1 for t, we will have this one. Do you remember sine of alpha was regarding to exponential function e to power of over 2j. So here I need one minus here, yeah. It should be, the positive should be e to power of jk omega 0 t t1, and this one should be minus. So which means I need to multiply it by 1 minus and 2j. In that case, this would be sine of k omega 0 t1. So I need to apply 1 over 2j. Since I added here, I should cancel it with the coefficient. So this one is here. Oh, my bad. This is minus 2j. I added 2j to the denominator. Here is minus 2j, which we have it here. And this is the from previous stage. So at the end, A curve would be something like this. We can define it with another function which we call it sinc. Sinc theta is sine of p theta over p theta. You can change this definition or notation to sinc. You can show like this one or this one, it doesn't matter, up to you. And function of sinc is something like that. As you can see, it's gonna damp when it goes to minus and positive infinity. So let's go to C1. Can you open path view? I want just to play some signal. Okay, let's okay, I need one sign input. One oscilloscope. Suppose I want to see how I can make this waveform using these sinusoidal coefficients. Okay. Now I have a sinusoidal output with the frequency of 1. I need to add another one. How much should I put its frequency and its amplitude? Anyone has any idea? I need to add this signal. Anyone have any idea how much should I put the frequency and amplitude? Same. If I write the same, okay, this is the same. You still have a sinusoid. But I want to make one square wave like the one I have here. So what should I do? I need to apply, yeah, the amplitude like AK, yeah, they are sinusoidal. I should apply like AK. For the first one, I just put it like 1. For the second one, it doesn't have, it has only for third one. And for the third one, it should be 1/3. If I apply frequency to 0 to 3 Hertz and amplitude to 1/3. It's a bit closer to square wave. For the next one, what should I add? How much should be frequency and amplitude? 5. It doesn't have even frequency, it's only 5. 5 and the amplitude 1/5. It's more closer, yeah. Again, next one, 7, 1/7. You can see it's getting more like square wave. I'm adding some sinusoidal signals, and at the output I have the square wave. When I can see one perfect square wave, how many sinusoidal should I add? Yeah. In theory, we should add infinite sinusoidal signals to see one square wave. Let me try something else. You cannot add infinite. How can you add infinite?
You is sinusoidal signals to make the square wave.
Yeah, you should at infinity to see the perfect square wave. But in fact, or in reality, we never go to that perfect. So we never have that much, and we never make a square wave like that. You will see, we make it really easier. Now suppose we have one square wave signal. Let me add one. So this is a perfect square wave. Yes. I want to see which frequencies are in this square wave. Yeah. You cannot see from time domain which sinusoidal this square wave has. What should I do? Let's go through one spectrum which shows the signal in frequency domain. Okay, I need to okay. I need to define frequency like this. From 0 to 10 frequency, 10 hertz and 100 samples. Yeah, that's what a spectrum is gonna look for. Let's read this one. You can see this. Let me increase the number, or I can increase the time better. Oh, couldn't wait. I need to add the more samples to see it more clear. Look at these peaks here. Which frequency is this one? 1 hertz. This spectrum is showing the signal in frequency domain. You can see here the horizontal axis is frequency. Yes. We have some peaks here, 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 and here. What are these? These are sinusoidal signals that they are generating this square wave. Suppose I want to find this sinusoidal. I can filter this. You just now, right now you have no idea about filter. Just know I want to just take this signal out, this one. I find one low pass filter. It's gonna filter the signal we should set. What is the, we want 1 hertz. Okay, let's put that filter. It's gonna filter the signal from 1.2 after. It keeps signal until 1.2 hertz and emit it after that. You can see the red line. You can see we don't have these peaks anymore. Yeah, but the first one, we still have it. See, it's gonna be something like sinusoidal, but since this filter is not perfect, let me increase its degree. If I increase to 4, it should be better. See, it's gonna be like sinusoidal. We deleted these other frequency. We just keep the first sinusoidal signal and emit other peaks. As you can see, the red line. Yeah, the blue line was the original signal. If I want to keep the second one, what should I do? I want just to see this sinusoidal. Yeah, I need one filter. We call it band pass filter. Band pass filter. How it works? I need to set the low band and high band that this band pass is gonna pass. The other frequencies is gonna delete it. We want the third harmonic, which frequency is 3. Let me put it 2 until 4. And I increase the order to have a really good filtering. You know, you see the green one, yeah? We only have this third harmonic. If I see in the time domain, the green line is the third harmonic, which means this square wave, it consists of different sinusoidal signals which we can obtain by filtering. Do you know any filtering? Have you ever seen? Can you make any filtering with electrical component? Yeah, if you remember, we had RC circuit, yeah? If I consider here as the output signal, if I see this output signal in a frequency domain, omega, if I change the frequency of the source, how would be the impedance of capacitor? It's gonna be decreasing, yeah? It's 1 over JC omega, that's its impedance. So VO would be something like this, yeah? For low frequency, VO is high. For high frequency, it's decreasing, which means we call this as a low pass filter. It transfers a low frequency to the output, but at the same time, it's emitting the high frequency. How about bandpass? We can add one low pass. Can I change this one to high pass? Exactly. If I just change the C and R and see the voltage of R, it would be high pass. How about band pass? We can add them, but one easy way. We had in electrical circuits. Do you remember this one? LC tank. If you see the frequency response, it's like that's kind of bandpass. You can set these ones with R, L, and we will learn about this after more. It was just how we can make filter. I cannot delete that. Okay, another example. They want us to write this xct in a form of Fourier series. How can we do that? We know Fourier series is e to power of jk omega 0t. I just need to change these values to exponential form of themselves. Now this is form of Fourier transform, yeah? Xt is sigma of some exponential signals, which are the frequency is a multiplication of the fundamental frequency. If Xt is real, A car should be conjugate of A minus car. As you can see here in the example, A1 and A minus 1 both are conjugate. Since this is a real value, its conjugate is equal to its original value. And same here, same here. If X is real, we can do that. Do you remember how we wrote X, the sinusoidal form of Fourier series? Yes, we wrote it like this. How did you find A0? That's a DC value. It should be. How did you find AN? 2 over T. Yes, and for BN, can we change this form to sinusoidal form? It should be, we should be able, if we cannot, something is wrong with math. It's really easy. I will ask you in one assignment to do that, how we can go through this one to sinusoidal form. That's easy. You just need to expand this e to power of j theta is cosine theta by plus j sine theta. You need just to expand through this relationship. Okay, as you saw, if I want to have really precise xt, I need infinite sine or cosine wave. Okay? If I don't have, it would be one error. You saw in the waveform I showed, and the energy of these errors shows how we are close to original xt or not. For example, this is what we were doing with path view. Suppose we have a square wave. If we estimated we only one sinusoid, how much is error? It's a square of these different areas, yes? If I add these areas together, square of this area. That would be error. For this one, it's getting less, yes? This area is getting less. The area of difference, yeah? xt minus its estimation. And here again, if I add the number of sinusoidal, you can see the error is, to get zero error, I need to have infinity. And we can find, for example, for 2% error, how many sinusoidal we should find through this relationship. We usually never do that. But Fourier series has one convergence conditions. You cannot define Fourier series for any signal you have. Yeah. Up to now, the only condition for writing Fourier series was, what was the only condition? Periodic. Yeah. The signal should be periodic. But not any periodic we can define sinusoidal. It should Fourier series. It should have some condition. The first one, its energy should be infinite. For example, this one energy is infinite. This one, can you see the thing? Yeah. You were looking at what you are talking about. There is nothing there. Is the energy finite or infinite? Infinite. Here the value is how much? It's going to infinite, yeah. You know, on -1, the value is exactly infinite. So you cannot write Fourier series for this one because its energy is unlimited. And on the other hand, we should have a finite number of maximum and minimum. It should be finite. The number of maximum and minimum should be limited. Here we have unlimited values, so we cannot write for this one. And the discontinuity should be again limited. We have unlimited discontinuities here. So the condition is, at first, the most important one, its energy should be limited. If its energy is not limited, we cannot define. We usually never see a signal like that or like that. It's rare, but we should check about this one. It's important. Okay, up to now, we could only move signals from time domain to frequency domain if they were periodic. What happens if the signal is not periodic? What is Fourier transform? Yeah, but what's different with Fourier series? Let's see how we do that. We have one non-periodic signal here. It's defined between -t1 to t1. I can imaginarily repeat it and make a imaginary periodic signal. It's not real. The real signal is this one. I call this as a XPT. Yeah. Now this is a periodic signal. I can write Fourier series for that. Yeah. For the original one, X1T, I couldn't because it wasn't periodic. I write Fourier series for this one. At the same time, I just need one period of this signal. The others I don't have. What should I do? If I don't want to see this one and this one, the original signal is this one, yeah? I imaginary try to make it periodic. At the end, if I want to reach to the original signal, I need to move this shape to infinity, yeah? Move this shape to infinity and this one to minus infinity. How can you do that? If I find the limit of T0 when T0 goes to infinity. This is T0, yeah. It's on me, yeah. I try to make it imaginary periodic. I can make that period infinity. So in that case, I will have only xt. Okay, I write for this imaginary signal the Fourier series. It's like that. And at the end, I find limit of T0 when it goes to infinity. Both signals would be equal. If we find T0 when it goes to infinity, A car would be how much? A car would be 0. But this integral, it's not 0 because we have xt. We know A car is approach to 0, but this value won't be 0. Why? Because of this side. Yeah, because we have xt, we know this integral is not 0. So we define this value T0 A car as x omega when we are approaching T0 to infinity, which means omega 0 is approaching to how much? Omega 0 is approaching to 0. Yeah, it's gonna get smaller and smaller. We can consider it as a continuous variable. So k omega self, we consider it as omega. And from series transform, we will have Fourier transform. How we find? We imaginarily make the signal periodic, find its Fourier transform, and its equivalent is Fourier transform. Okay, this is the definition of Fourier transform. This is the inverse Fourier transform, how we can, but we never use that. How do you find inverse Fourier transform? You had this course before, you have seen it. How do you find? Based on properties, yeah? After that, we will see this transformation has some properties. We find the inverse Fourier transform using that properties. Okay, I know here a omega is T0 A car. So if I have a periodic signal, if I have this signal and I want to make it periodic, I can easily find its Fourier transform and change omega to k omega 0, which omega 0 is 2p over T0 Depends on the frequency you are trying to make it periodic, and one coefficient which is the fundamental period. Yeah. So you can, after that, it's easier to find Fourier transform rather than Fourier series. We can easily find Fourier transform and apply this formula to find the coefficient of Fourier series. Do you remember this shape? Yeah, we find it Fourier series for that. Right now we can easily write its Fourier transform. You can see it's much easier to find Fourier transform. And if I write k omega 0 instead of omega and divide it by t0, I will reach to coefficient of Fourier series. Okay, let's see some examples together. I have a signal like this, exponential e to power of minus AT. A is positive or negative. What's the difference if A is positive or negative? Suppose if A is positive, I would have e to power of 2t ut. If I want to draw it, yeah, it's increasing. Can I define Fourier series or Fourier transform for this one? No. Why? Yeah, exactly. Its energy is not limited. Yeah, it has infinite energy. So I need to. So the only condition is this A. It should be, this coefficient should be negative. Yes, which means here A should be positive. It would be something like that, which energy is limited value. So I can define Fourier transform for that. So if we write the relationship, it was x omega was minus infinity to infinity xt e to power of positive or negative? Negative. D omega or t, I want to keep omega, so it should be t dt. What is xt? E to power of minus at ut. Ut means, yeah, it's from 0 to infinity. So I should change the starting point from 0 to infinity. Now I would have this integral. You can e to power of alpha t. Yeah. E to power of alpha t is 1 over alpha e to power of alpha t. If we sub t by infinity, e to power of minus infinity is 0. Yeah. E to power of 0 is 1. It should be 1 over a plus j omega. For me, it's easy to memorize this one and use it in another Fourier transform we are gonna do. Do you want a break? I'm seeing from your face. So do you want to short break? What time is it now? We have 10 minutes. Do you want me to continue 10 minutes? No, but oh, okay. I thought you were saying no, don't continue. Yeah, let's go a bit more. We have 10 minutes. After that, these are examples. Okay. E to power of minus a absolute of t. So I should break these abs to positive and negative side. Minus infinity to 0. It should be t should change to minus t. I have another negative here, so it should be positive. From 0 to infinity, t comes out with positive sign, so it should be e to power of minus 80. Again, e to power of alpha t, we know it should be the answer of the first part. The answer of the second part is e to power of minus, which is 1 over j e to power of 0 to infinity, which is 1 to a power of j omega. And I think I made a mistake. This one is for this one. This one is for this one. And the answer would be something like that. Fourier transform of delta is delta multiplied by anything. It's gonna be sampling. Yeah. Take it at where delta is defined 0. So anything who is multiplied by delta, which is only this one, I should just put t equal to 0, which means e to power of 0, which is 1. So this one should be 1. Delta minus infinity to infinity delta t is equal to 0 minus 2 delta t. They are the same, yeah? Why? Because delta is defined only in one point. From 0 minus to minus infinity, its value is 0. From 0 plus to 0 to infinity again, its value is 0. I only have delta in a short period of time, which is here. Here, it's the area under its curve is 1. Yeah, this integral is 1. The convergence is exactly like Fourier series because we find it through Fourier series. So all conditions for convergence, which we saw earlier, should be same. If I add, the Fourier transform has linearity property. What does it mean? If I have j, if I have e to power of minus 2t ut, what is the Fourier transform of this? What is a? J omega plus or minus plus or minus plus by this root should show this coefficient. If you find this root, which means you should put it equal to 0, j omega should be minus 2. So this should be minus 2. So if I multiply this one by a coefficient 5 e to power of minus 2t, what would be the Fourier transform? Because that's linear, yes. If you multiply input by a factor, the output or its transform should be multiplied by 5. If I have minus 2t ut plus minus 5t, not plus, minus. How do you find this one? Yeah, since system is linear and Fourier transform is linear, we can find this separately, and add the answer. This is 1 j omega plus 2 minus 1 j omega plus 1. This is the linearity property, which makes it really easy to find. Okay, as an example, who can tell me e to power of 5t u minus t? What is Fourier transform of this waveform? How do you find it? We just know the relationship. U minus t is defined exactly e to power of 5t e to power of minus j omega t d. It is e to power of 5 minus j omega, which is 1 over 5 minus j omega e to power of 5 minus j omega. If I sub t with 0, it would be, if I replace t by 0, it would be 1 minus, if I replace t with minus infinity. Why 0? I would have 5 minus j omega in minus infinity. Yeah, that's it. How can you say this is 0 or infinity? I can write 5 minus infinity multiplied by infinity in j omega. Yes. E to power of j omega t was cosine omega t plus j sine omega t. Now for t we wrote infinity, which this is cosine of infinity plus j sine of infinity. We know cosine and sine are limited value. Yeah, it doesn't matter how much is they alpha. If we change alpha to infinity, it doesn't matter. It would be between -1 and 1. This value is limited number. This value is limited number. This value is limited number. Yeah, which means this one is a limited number. Its absolute is almost 1. How about this one? This one is 0. Yeah. 0 multiplied by a value should be 0. So when I put minus infinity, it should be 0. 1 minus 0, which is 1 over 5 minus j omega. we have different, I'm gonna go through another properties next session. I think it's enough for now. If too many, you will be so tired. Any questions up to now? If they are so simple for you, I can go faster. If you think that's a bit difficult, I can slow down. Just let me know if you think it's really fast or really slow, because I'm not in your mind. I have no idea. Are you able to catch up or not? Just let me know. Any question? We have example. No? Oh, I got what you mean. You wanna write down by yours. If I solve here, you just see it going fast. And that's true. I'm trying to do that, but every time I'm asking you, I'm waiting, but it's okay. I think I should do it more frequently. You are right. We will do it from next session. Yeah. If you think that's faster, so just let me know. The goal is learning. It doesn't matter how long it's gonna take or not. Important thing is we are putting our time, we are spending our time together here, and the main thing is we should learn these topics that it makes us ready to go through some advanced topic to design how we design IC. Okay. Thank you. Any other comment? Thank you very much for coming. Please go through the assignments to assess yourself and see how can you do well. If you had any question, please feel free. Don't hesitate to reach out to me. I will try to help if I can. Thank you very much. Okay. After reviewing last we found it. Some of them yeah. Some of you maybe going so we are going to be fine. We are continuing this formal longer. After devices, we go through circuit. After and then that end of having all people that suddenly people out of the general that's all for human is that you can think you need all of it. Right now everyone is literally understand that you but if you use them we are using it. I got because I had to find how I can find the check for the director. Make what in our job we are making money for some people in Oman people are arguing. Making it when you okay, sure. It's better for you.
That's so what's the point? This book. So like for you that are you going like
For us,
yeah.
we are going to hire 10 to
By the end of this course.
for that train.
Yeah.
We are going to hire should make sure. Okay. I'm talking about if it we have to and that's the whole we are we should do that training and the whole
Brother.
everyone can join. We someone I was thinking and I shared. I thought job maybe, but I'm thinking with them, maybe we can have them as a part-time. But they're gonna graduate in 1 or 2 years. They're gonna have to take 1 year, but it should be 1 or 2 years. Of the life. That's bad.